Okay, so I have a small class of 9 students. They're arranged in a 3x3 grid, rows and columns. I wonder if sitting to the closer to the front causes the students to get a higher grade on the next test. She randomly assigns them to rows, teaches the lesson, Miley, and then records their scores on the test. So here's the table, okay? This is the row they were assigned, and then their scores. You see it? There it is. So let's just think for a second. Is this an observational study or an experiment? How do you know?
She's sending a treatment.
Yep. It's an experiment. There is a treatment. What is the treatment in this one? The row. Okay? Row assigned. Then why is it important to randomly assign the students to their seats rather than just letting them choose? Yeah?
They might self-select into...
Yeah. Think about the ultimate conclusion we want to make here with an experiment.
You want to apply it to like all the other students.
Okay. If it's random, that's what happens if random. We can generalize to the whole population. The random assignment piece, you may not remember this from chapter 4. It's been a minute. The random assignment's important because we want to be able to conclude a causation. The row causes the grade. You can't do that without random assignment. Okay? So it allows us to show causation. All right? Now, how many variables are we dealing with here? Don't overthink it. Just look at your table. 2 variables, which are row and score, right? Are they quantitative or categorical? Are they? Quantitative. Quantitative, yeah. Quantitative. So which of our 2 variables is the explanatory?
Explanatory is row.
Is row, And the response would then be score. Nothing new so far, right? This is all chapter 3 on repeat. So here's the dot plot. Here's the equation. It's provided for us. Interpret the slope of the LSRL, the regression line, in context. So what is the slope of this line? Look at the equation right there, guys.
It's a slope of 3.
-3, right? -3. Y'all see it? You didn't have to calculate it. It's just right there. All right, so if I interpret this is on your test Friday, so let's see, can you remember how to interpret slope? I heard that.
For each row, it decreases by 3.
For each additional row, a student's predicted score, right? Gotta have that word predicted. Will what? Decrease or increase?
Decrease.
Decrease by 3 points. You don't want to say decrease by -3. No. Decrease takes care of the negative, right? Use your thinker. You can do this. All right, that's just repeat. Now look at this. Does this negative slope provide convincing evidence that sitting closer causes higher achievement? Or is it plausible that the association is purely by chance because of random assignment? So, short version, do we have enough evidence to say that the row causes the grade?
No.
Why not?
Because there were only 3 people assigned to each. Not a large sample size.
1 sample of 9 gave us 1 slope. You think that's the real actual slope? No, it's not enough information, is it? We know this by this point in the course, right? We have to have a lot more, right? So, could be by random assignment. we need more trials, which will provide us with more information to see if there is a pattern, yeah? Okay. So we're going to simulate that really quickly. What you're going to do, whoever's helping me, you want to help me, Ryan, on the second one?
Yeah.
Lovely. Okay, so in your stat edit, in your table, go to L1. And so we have 9 students. So you're going to do just like this table says. L1 is going to be 1, 1, 1, 2, 2, 2, 3, 3, 3. Okay? 1, 1, 1, 2, 2. We're gonna create. What I've done is take those 9 scores that were in that sample and put them on little pieces of paper. Okay? I'm putting them face down. And what I'm gonna do. I need 2 volunteers to help me with the trials. Who wants to help? Is yours entering in the calculators for me? Nobody wants to help?
I'll do it.
Thank you, Sophia. I appreciate it. So, you don't, oh, you have a calculator. Okay. You just need a calculator. So what I'm going to do is, like in the 2, 3, 3, 3. Now, I'm going to call out the grades, and we're just going to start, we'll start with Sophia. And this is going to start at the top of your row 1, and you'll just fill it in from there. Okay? Does that make sense? All right. So your first grade is 86, 84, 83. Moving to row 2, 94, 86, 81, 85. 90 and 88. All right, so you're going to find the regression line for me and find that slope. And let me know what the slope is when you calculate it. Remember, stat, calc, number 4, and then let me know what slope comes up.
Our slope is 1.66666.
Positive?
Yes.
Okay. 1.66. All right. There's another sample. Okay, Ryan, you're going to do the same thing. I'm going to call them out, and you're just going to enter them in your list. List 2.
2?
List 1 should be 1, 1, 1, 2, 2, 2, 3, 3, 3. Yep. Okay. So this one is 88, 86, 81, 90, 83, 84, 85, 86, and then 94.
Is that right?
You're good.
All right. There we go. Our slope is. I think I did the wrong one. It's line red, right?
Mm-hmm.
B would be 83.
Is that the variable with X at the top of the screen?
I think I'm on the wrong one. Let me see.
Just look at the top of your screen. Which one has A is with X? So A is my slope. So 1 point. Oh, you got exactly the same thing. Wow, 1.66 again.
How do we use?
I don't know. You put in the trial 2 data, right?
Yeah, for list 1, 1, 1, 1, 2,
Uh-huh.
2, 3, 3, 3, and then the numbers you repeated and.
I mean, that could happen, right? It's possible. Crazy though.
Yes.
Unlikely, but it happened. Okay, so what we have down here is a dot plot, and what they've done is done the same thing we just did 98 more times for us, saving us some quality moments. And so what the dot represents is the slope that they calculated from their 98 other trials. All right, we're going to add the 2 that we found. They just happen to be the same. 1.6 probably sit up in here somewhere, right? All right. So now I have 100 samples to choose from, right? And what percent of these 100 had a slope, remember the original was -3 or lower? How many of those have -3 or lower? Only 4. Only 4 out of 100, which would give me a p-value of 0.04, right? Now, think back to your hypothesis testing days. Is that convincing evidence if p-value is 0.04? If alpha is 0.05, right? If alpha is 0.05, then yes, this is convincing. But what about if alpha was 0.01? It would no longer be convincing, would it? So it depends on alpha. Then maybe the row has something to do with the score. So what we're doing in section 1 of chapter 12 is looking at the slope of regression lines. And remember, slope is positive or negative, right? And that shows an association between two variables, right? So when we start talking about slope, we're looking at the relationship between x and y. Is it a positive relationship or a negative? So we're going to do a confidence interval for the slopes. We're trying to predict what is the true population slope or relationship between these two variables. And then we'll also do hypothesis testing. So it's going to do all the things that we've been doing just now with slope. All right? So on that, I'm going to show you some new symbols. It'll remind you of some symbols. So in our last chapter, we dealt with the sample. So we said it was y hat equals a plus bx, right? That's what we're used to. And what was the y-intercept in that line? A. Slope was b. Standard deviation of residuals. Do you remember what symbol we used for that? It was just S. And standard deviation of slope. Now, we didn't really mess with that in the last chapter, so it's going to be SE, the standard error of little b, slope. Now, that's the sample. Remember, one of the main ideas of statistics is to take a sample so we can make inferences about the population, right? Make inferences about the whole population. So we need to rewrite our equation so that it reflects the population. So we would say this. The mean of the y's equals, instead of little a, we use the alpha. Now it doesn't mean significance level here. It means y-intercept, the true population y-intercept, plus beta, it's big B with a little tail on it, x. So my parameters get new symbols, right? Alpha, beta, sigma is standard deviation. We're used to that. And then this would be sigma of b. You don't really see those very often, but they're there.
Wouldn't it be sigma of beta?
Beta. Little b isn't beta. It's, I don't know if it's called something different. I don't know. I thought big B was beta and the little b gets a different name. Maybe not.
Beta,
Beta, eta. Itty bitty beta. I don't know. There you go. Now, sampling distribution of B. Well, slopes are going to follow normal distribution. That's all we're going after there. Okay? So let's not worry about that section. Now let's look at this problem. You may have heard that your nose and ears grow throughout your whole life. While it is true that your nose and ears get bigger throughout your life, it's not because they grow, it's because of gravity. The cartilage in your nose and ears breaks down as we age, and the growth that people observe is the result of drooping. To quantify the expansion of ears over time, a random sample of 30 adults were selected. For each adult, in their age in years was recorded, and their ear height, who knew? Ear height in centimeters, I know, was measured. Below is the regression output. Is there evidence of a positive linear relationship between age and ear height? Assume the conditions have been met. We'll deal with conditions in the next one, so don't worry about that. Now, look at this. What is here's this table of stuff, right? Where's my y-intercept?
Constant.
Yep, this is my y-intercept, right? And where's my slope?
H.
Okay. So that's telling me slope is my explanatory, right? Yeah. Okay, so now it says, what's the estimate for alpha? Since it says estimate, all we have is the sample information, right? Our estimate for alpha, alpha stands for y-intercept, right? So the best we can do for alpha is 2.8871. Then it says interpret. Okay, let's see if you can still remember how to interpret from Friday. So a y-intercept is when x is 0. So what does x represent here? Age. So when the age is 0, that's birth, right? So when age equals 0, we predict the ear height to be 2.8871 centimeters on average. Is that reasonable? Maybe? That's kind of seems like a big ear for an infant, doesn't it? Maybe. It's not negative. That would be irrational, right?
There's gonna be a lot of Dumbo babies.
Dumbo baby. But this is just an average, people. This is an average, okay?
So they're bringing it up, the Dumbo babies.
Right, Dumbo babies. They got to include the Dumbo babies. Yeah. All right. So then what is the estimate of beta?
It's our 0.001 or 21.
That's our slope, right? 0.0021. That's our best guess at slope, is little b. So if we interpret slope, we say for each additional, what? Yep. Year of age, we predict the ear height to increase or decrease? Increase by 0.0021 centimeters. Bless you. Okay, now estimate for sigma. What does sigma represent? How's it represented in my table up here?
S.
That's S. And where's S? Right there at the bottom, right? 0.3613. Remember, S stands for the standard deviation of the residuals, right? Residuals. And when we interpret that, we start with our actual response variable, which was ear height. So we would say the actual ear height typically varies by 0.3613 centimeters from the predicted ear height. Not too bad, is it? Nope, everything's been reviewed so far, right? Now, D gets a little weird because this is the new one. It's the standard error of the slope. Standard error of the slope. So this slope is from our sample, right? Standard error means how far is it different than the true population slope. So we haven't used this verbiage yet. This is new. We can do this because it's going to be the typically varies scenario again. So we would say the slope of the sample LSRL typically varies from the slope of the population, LSRL, by about, and it's this value right next to your slope under the SE coefficient. That number right next to the slope is your standard error of your slope. 0.0059 centimeters per year. And using that unit of centimeters per year, that gets your context in there, okay? That's your context. Now, up in your table, this is the standard error of your slope. If we needed it, this would be the standard error of the y-intercept right above it. We don't ever really use that standard error for y-intercept, but the standard error of slope is there and you will need it. But the nice part is you don't have to calculate it. It's done. We okay so far? Okay, now, moving on, that's your introduction to the slope stuff.